السلام عليكم. بسم الله الرحمن الرحيم. الحمد لله والصلاة والسلام على رسول الله. Yes, we start now another lecture. Okay, we'll start chapter 5. Chapter 5 is talking about thermochemistry. Okay, and what are we going to talk about? We're going to talk about the relation between heat and chemistry. And of course, heat is energy. Good. Now, what are the forms of energy? We have energy. We have three forms of energy. We have kinetic energy, which is related to motion. And always the law is E equal to half mu squared, where U is velocity. Velocity, that's well known. Keep it in mind. That's first one, which is called kinetic energy. Kinetic energy. Good. Second one is called thermal energy, is one of the kinetic energy, one example of kinetic energy, and it's related to temperature. So when you measure the temperature of anything, you are calculating the kinetic energy, which is thermal energy. And in this section, thermal energy, we're going to use it a lot. And the letter that we're going to use for thermal energy is Q. And for work, we have also work, we have the kinetic energy, work, the other important energy, and we're going to represent it by the letter W. So thermal energy is Q and work is W. Both of these are kinetic energy. And Q, we measure Q by actually measuring the temperature change. Now, next, we have another kind of energy, which is called potential energy. Potential energy is related to position. We usually represent potential energy by two lines, in which this line is higher in energy than this line. So if you go from this place to this place, then you are going from higher energy to lower energy, and energy will come out of the system. Energy will come out of the system. But if you go from here to here, then you need to put energy, you need to add energy, potential energy. You need to add energy to go from lower potential energy to higher potential energy. Okay, the potential energy that we're going to see here, two important ones. First one is U, which is internal energy, and the other one is H, which is, we're going to use a lot here, which is called enthalpy. I want you to memorize these two names, and both of these names are potential energy. Potential energy. Okay. These two letters you must memorize very, very well, which is U for internal energy and H for enthalpy. The chemical reaction and chemical energy, okay, which is the arrangement of all the structure, the shape of the molecule and so on, is actually kind of potential energy. And so all the chemical reactions are related to potential energy, and we're going to calculate the enthalpy and the internal energy of these chemical reactions. Third type of energy is called electrostatic energy, which is related to attraction and repulsion. And this is the law for this energy, okay, in which Q is the charge on the molecule. So if we have Na plus, what's the Q for Na plus? It will be +1. How about if we have Cl minus, Q2 for, or Q for Cl will be, this one is +1, this one is -1, and so on and so forth. For example, Ca2 plus, it will be +2, and for N3 minus, it will be -3, and so on and so forth. And D is the distance between the two atoms. Usually this is for ionic compounds, and the D is the distance between the cation and the anion. Good. Okay, we have a law of conservation of energy similar to the law of conservation of mass. We remember law of conservation of mass, we took it in chapter 2. We have same law for energy. You can never lose or create energy. Energy can be transferred from one state to the other, but you can never lose or create energy. This is the law of conservation of energy. Good. Now, I want to define two things: system and surrounding. System, you define it yourself always, and anything that, for example, I want my system is this box, then this is my system. Whatever around it is surrounding. System, and whatever around it is surrounding. Okay. In our case here, most of the time, our system will be the chemical reaction. For example, H2 plus O2 to give you 2H2O. Where is my system? The system is the chemical reaction itself, and the surrounding is anything around it, whether it's if it's in water or in air or whatever. So the chemical reaction is the system. The chemical reaction itself is the system, and anything around it is the surrounding. Good. Now, heat, which we represent by the letter Q, you have to keep it in mind. Heat is related to motion. It's kinetic energy, and we are going to represent it by the letter Q. All right. And when we say thermochemistry, as we said, it is transfer of heat from one system to the other. That's thermochemistry. Now, if we have a chemical reaction like this, then we're going to call this enthalpy. The energy here related to chemical reaction is called enthalpy H. Enthalpy. And in this case, we are going, this is the reactant, and this is the product. We're going from higher, where is my system? The system is the chemical reaction itself. Now, in this system, we're going from higher energy to lower energy, so energy will be given out as heat after the system. Okay, so the difference in between these things, actually, this is, I wrote, the difference between these two is the delta H. Delta H is the difference between these two states, and the energy that will come out here, actually, I should make a mistake here. This energy is actually heat. The energy that will come out is heat. So delta H, calculate the difference between the reactant and the product, and the Q is the heat that will come out of reaction in this case. In this case, in the contrary, I need to add Q here to go from this place to this place, and the difference between these is the enthalpy. Delta H. And this energy here is Q. I need to add Q to the reactant to make the product. And this process is called endothermic. If you add energy to the reactant, then this is called endothermic. While if you get energy out of the reaction, then this is called exothermic process. So this process is called exothermic. This process is called endothermic process. Good. The unit that we're going to use for energy is joule, and keep this in your mind very well, that 1 joule is equal to kilogram times meter square over second square. Very important to remember this thing. Now let's do calculate the kinetic energy for helium atom moving at speed of 125 meters per second. So what's the atom that we're going to have is helium. What's the mass of the one atom helium? It's actually 4.003 AMU. And I need to change AMU to gram. How? First, I multiply by 1 gram is equal to 6.022 times 10 to the power 23 AMU. And now I change it to gram, but I need to multiply then by 1 kilogram is equal to 10 to the power 3 gram. Gram will grow with gram, and now I have the mass in kilogram. And the speed is 125 meters per second. So the energy will be equal to the mass that you get from this reaction in kilogram times 125 square, and you have the answer. Okay, now we have here another thing, which is electrostatic energy. We remember that energy is proportional to what? Q1 times Q2 divided by D. If we have the same distance, but we change the nucleus from containing 1 proton, 3 protons, to another nucleus that contain only 1 proton. What will be the difference? In the first case, if we have 1 proton, then the E will be 1 times 1 divided by D. If we have 3 protons, if we have 3 protons and 1 electron, there's 1 proton and 1 electron. But if we have 3 protons and 1 electron, then it will be 3 times 1 electron divided by, if it's the same distance, then which one will be higher? This one will be higher. How many times? 3 times. Okay. Now, another unit that we're going to use a lot is calorie. Everybody is familiar with calorie, and calorie is equal to 4.184 joule. Don't memorize this number. It's available for you in the periodic table. If you go to the periodic table, we are providing you with the different change between calorie to joule. We sometimes use capital calorie to mean 1,000 calorie, and in this case, 1 calorie will be 4,184 joule. Next. Okay, we have what's called open system, closed system, isolated system, and this is the example of this is open system, open. This is closed. And this is isolated. Isolated, why? Because no heat will come out because it's insulated like this. Heat will come out in this case. Good. Okay. Now, we also have, I want to define another thing, which is state function. Very important word, state function. State function is, this means there is there is certain values that depend on the state where the reaction is. I mean, if we have a chemical reaction, we have state function, like, for example, energy or pressure or volume. These are state function. State function, what's that mean? If we have a system at a certain temperature and certain pressure, it will have a certain value of volume. It will be exactly, if we talk like chapter 10, if we have a gas at certain temperature and certain pressure, it will definitely have a certain value, a volume. The volume here is called state function. It will be exactly the same volume regardless from where you bring the reaction. I mean, the gas. But you have to have this gas at a certain temperature, at certain pressure. It will definitely have certain volume. This is called now state function. I just want to say that volume, pressure, temperature, also enthalpy, and U are state function. This means they will have a certain exact value if we have the same temperature and the same pressure and the same, all the factors are the same for these things, then these are state function. While there is no state function for Q and W. Q and W, it depends on how you take these things. So Q and W are not state function. Q is heat and W is work, are not state function. H is enthalpy and U is internal energy. And these are state function. And of course, volume, temperature, pressure are all state function. Now, first law of thermodynamics, it says very simple law. First law of thermodynamics, it says that delta U, which is the internal energy of the system, plus the internal energy of the surrounding must be equal to 0. This means you cannot gain or lose any energy. All the energy that will be lost, law of conservation of energy, all the energy that will be lost from the system, it will be gained by the surrounding. And that's why the state of the system must equal to the state of the surrounding with the negative value, so that the total, if you add these two together, it will be exactly the same, and the total will be 0. And of course, we always take delta U. We know that delta means final minus initial state. Okay. Delta U, the energy, which is, we said this is state function, but actually there's another way to say the first law of thermodynamics. Also, the internal energy must equal Q plus W. All the energy that will be lost here, for example, will be gained by heat and work, or any energy that you lose in Q and work to be gained by delta U. Okay, now we're going to give values for heat and work. For example, if the heat is absorbed by the system, then we will give it a positive value. If the heat is released, so if this is your system, if you add heat to the system, then the Q will be positive. If this is your system and it gives heat, then this Q will be negative value from system to surrounding. Of course, if this is system and this is system, in this case, the heat goes out from the system to surrounding, then Q will be minus. And if it's again from the surrounding to the system, then it will be positive. For the work, if the work is done on the system, like for example, this is my system, and I do work in it, for example, I put pressure on it, then work will be positive. If the work is done by the system on the surrounding, then W will be negative. There's another system. When the work is done out, this means W is negative. Let's have this example. To calculate the overall change energy, if, of course, we know that delta U equal to Q plus W. What will be the value of that? If there is absorbed, the system absorbed, this means the heat come from the surrounding to the system, and that's why the Q will be positive 188. And the system does work. This means the system does work in the surrounding. So W will be in this case what? Negative. So delta U will be positive Q with and negative W, and the total will be like this. Okay. Now, if we have a chemical reaction, any chemical reaction, then we're going to calculate all these things. And what we are going to talk about, I'm going to define two things now. What's Q? Q is heat. We have two types of heat. We have QV, which is no change in volume, constant volume. Then QV always equal to delta U, equal to the internal energy. If you don't change the U, the volume. Okay, so this is the case. Why? Because delta U, first I have to say that work actually is equal to minus P delta V, always the change in pressure, like in this case. So if we have the work in a piston like this, if the work is done up, then the work is done by the system on the surrounding, and that's why the work will be negative, and it will be equal to P, which is the pressure, times the change in the volume, which is this value. This is the change in volume in this case, which is from here to here. And that's why W is equal to minus P delta V. Okay, so if delta V, there is no change, this means this value is 0. And in this case, delta U will be equal to V. And in this case, since there is no change in volume, we're going to call this QV. At the same time, if there is no change in pressure, then this value, if there is no change in pressure, there is change in volume, but there is no change in pressure, then the QP will be equal to the enthalpy. Enthalpy. Good. Now, enthalpy, delta H, is always equal to H of products minus H of reactants. As we said, enthalpy is potential energy, and this is the energy here, and always we're going to have it like this, and we're going to have the reactant at higher energy for here in this case, and product here. This means you're going from reactant to product like this, then this delta H will be negative value. On the other hand, F and Q will come out of the system. Q, which is heat, will come out of the system. On the other hand, if this is the reactant and this is the product, then you're going to go from here to here. Delta H, which is the delta H of product minus heat of reactant, you need to add energy to it, and in this case, delta H will be positive value. Positive value. So if we have any chemical reaction, this means minus 890.4. What does that mean? That if we have reactants, the reactants are at higher energy than the product, which is CO2 plus 2 H2O. So if you go from here to here, you're going to give out energy. That's why it is negative. That's the negative. And the value of the heat that will come out will be 890.4 kilojoule per mole. And I can relate this now. This means 1 mole of this one will give me, will need 2 mole of this one to give 1 mole of this one, and 2 mole H2O, 2 mole H2O, and the heat will be minus 890.4 kilojoule. So 1 mole is related to 890.4, or I can say also 2 mole of O2 is also related to minus 218 mole, or 1 mole of CO2 is also related to the same heat, and 2 mole of H2O is related to this heat. So if I give you only one of them, you can calculate the heat easily. Let's solve this problem. In this case, of course, which one is higher in energy? The reactant is lower energy than the product, so the H2O solid is here, and H2O liquid is here, and I need to add energy to go from here to here. That's why Q is positive, and the value is 6.01 because I added energy. Good. Okay. When you reverse any reaction, for example, in this case, if I reverse the reaction, I want to go from H2O liquid to H2O solid. Okay, this means heat will come out of the reaction, which is exactly the reverse of this one. So the Q will be exactly the same value with a negative value. And that's why if you reverse any reaction, this means you're going to reverse the sign of the reactant, of the delta H. This means H2O liquid goes to H2O solid, and the delta H will be exactly equal to minus 6.01 kilojoule per. Okay, same thing with this one. If I reverse the reaction here, this means I go CO2 plus 2H2O to give you CH4 plus 2O2. This means delta H will be plus 890.4. And if I multiply everything by 2, for example, I want 2 CO2 plus 4 H2O to give me 2 CH4 plus 4 O2, then delta H will be, in this case, the delta H will be twice the amount of this one, which is, well, of course, it is plus because I did not change the reaction state, and it will be plus 2 times 890.4. I wish you understand this. Okay, calculate now the heat required to synthesize 75 grams of this one. We know that now I want only 75 grams of this one. I know from this chemical reaction that 1 mole of sugar will need 4,803 kilojoule per mole. So kilojoule per mole. Okay. Then how much energy I'm going to get if I have only 75 grams of sugar? I need to change the 75 grams of sugar into mole, and they have this reaction. And then from the chemical reaction, I know that 1 mole sugar will need 2803 kilojoule. Then if I have 0.416 mole sugar, how much energy? You multiply this by this and divide by this one, and you'll have the energy. Okay, and with this, we'll stop here for this chapter.